All right. So welcome back, everyone. And we'll have Patrick Hayden's second lecture on the introduction to quantum information.
All right. We just had a little discussion about protocol for asking questions. And so I just wanted to, I guess last day I said that you should raise your hand if you wanted to ask a question, but feel free to just break in and interrupt me if you have a question. If it gets out of hand, we can revisit, but it should be fine. Now we ended last day with the worksheet, and so I wanted to go through the worksheet just to make sure that everyone was on the same page for that. So that's the first thing we'll do today. So I'll share my screen. Okay. And if you remember, this was a situation where Alice and Bob were sharing this maximally entangled state, 0, 0 plus 1, 1. And the first question, part A, was just asking what happens if Alice measures in this 0, 1 basis. I mean, it's pretty clear it collapses that superposition onto either 0, 0 or 1, 1, each with equal probabilities at a half. And so with probability a half, Bob gets a 0, and with probability a half, Bob gets a 1. Now, for part B, it turns out it's pretty much the same question because this state can be rewritten in this plus minus basis, this basis right here, as again, plus plus summed with minus minus. And this state is not quite rotationally invariant. It's not the singlet state, but it has some amount of rotational invariance. And so it has that symmetry. And you can just verify that by calculation. If you expand this out, then the cross terms will cancel and go away. And so just by exactly the same argument as in part A, if Alice measures in the plus minus basis now, Bob will end up in either the plus state or the minus state. So with probability a half, Bob gets plus, and with probability a half, Bob gets minus. Now in part C, I'm asking you, I say, well, imagine that this ensemble ambiguity property that we saw for density operators. And just to remind you, what I meant by that was that for any given density operator which isn't pure, there is an infinite number of different ways as writing it as a mixture of pure states. We saw that the maximally mixed state could be an equal mixture of up and down, or of left and right, or a uniform mixture over the entire set of pure states, that there are an infinite number of ways of writing any mixed state which is not a pure state. And so I'm just saying now, hypothetically, thought experiment, imagine that wasn't true. Imagine that given a preparation of states according to some probability distribution, that every preparation was distinguishable in some way. There would be some experiment that would just, that would tell any pair of preparations apart, even if they had the same density operator. In that case, that would give us a way for Alice to send a message to Bob superluminally. If she wanted to send, say, 0, then she could measure her half of that entangled state in the 0, 1 basis. And if she wanted to send a 1, she'd measure her half of the entangled state in the plus minus basis. And from parts A and B, depending on which basis she measures in, Bob gets a different ensemble of pure states in his lab. Now, in actual quantum mechanics, the density operator associated with those ensembles, two ensembles are the same, and so Bob can't tell them apart. But just by hypothesis here, if there were not that ambiguity for different ensembles, then he could tell them apart, and then this would be superluminal signaling. Now, one way that can happen is if Bob had a cloning machine.
Can I, sorry.
Yeah, sure, break in there. Yeah.
Okay, yeah. So it seems like the information that Alice is giving to Bob is which basis she's measuring in, right?
That's right.
Okay, so, but wouldn't that require, in order to make any information out of that, some kind of classical communication about an encoding information? So what does it mean to measure one base? What does it mean to measure the other base?
Well, it's just depending on the action Alice takes, Bob has two different situations in his laboratory, and he could measure them. Now, my question was a little bit vague here, whether he could perfectly distinguish those situations or just partially distinguish them. Like that sort of, I didn't specify. So we could just imagine, we could say, imagine he could perfectly distinguish them, and then we'd be done. And it's more precise, I guess, in parts D and E. So part D is asking, why can't you clone in quantum mechanics? And I imagine most, if not all of you have seen this before. A cloning operation is just one that takes an arbitrary quantum state phi, so it has to work for any quantum state, and takes it to 2 copies of phi, phi tensor phi. And this is prohibited because it's nonlinear, right? If you think of it in terms of the coefficients expanded in some basis, phi tensor phi is quadratic in those coefficients. And so it's not a linear transformation. So that's not something that quantum mechanics can do. But we can just say, well, imagine Bob had one. How could Alice and Bob use that to communicate superluminally? Well, Bob would just clone the state that the state in his lab repeatedly. And so the cloning operation has to, the 4 possible states Bob could get are 0, 1, plus, and minus. And if he clones 0, he gets many copies of 0. If he clones 1, he gets many copies of 1. If he clones plus, he gets many copies of plus. If he clones minus, he gets many copies. Oops, typos. If he clones minuses, he gets minuses. He doesn't get pluses. And as the number of copies goes to infinity, so I should label the number of copies here, Bob's states become orthogonal, right? And so you have 4 states in some large Hilbert space that are becoming orthogonal. And so there's a measurement that Bob will be able to perform that will be able to distinguish them. And the probability of error, if you analyze this, will go to 0 exponentially with n. And so if you could clone, then you could communicate superluminally. And the moral of this story, well, what is the moral of the story? Part of the moral of the story is just that this ensemble ambiguity is an essential part of quantum mechanics. That in creating if you want to be able to create a consistent relativistic theory of quantum mechanics, this ensemble ambiguity is essential. That without it, you're going to have superluminal signaling. And so that's part of the message. These thought experiments involving cloning and measurements and communication, they have a long history also in quantum gravity, going back to Preskill and Page and Susskind back in the early 1990s and the black hole information problem. All right, so different thought experiments, but thought experiments of a somewhat similar character. Sergio, go ahead.
Yeah, so I was just thinking, can I think of the ensemble ambiguity as the fact that because the block sphere is not a simplex, points inside do not uniquely specify ensembles? Yeah,
it's as simple as that. So it's a mathematically trivial fact, but physically it has very important consequences. Yeah. Mm-hmm. Okay. So now, the original copy of this lecture was going to be entropy, but given that we went a little bit more slowly yesterday than I had anticipated, I've revised the title to be the more general topic of measures of information. And what we'll start with, so we're going to start off with distance measures, in particular distance measures for mixed states, and then we'll move on to entropy and its properties and things you can do with it. Now, why do you want a distance measure, right? You could just, you could write down some arbitrary metric on mixed states and you just work with it, and that should be fine. But when we're doing pure state quantum mechanics, the inner product plays a distinguished role, right? The inner product is a measure of the distinguishability of 2 pure states, and we use it all the time. And so if you're going to be thinking about, and somehow the inner product is the source of all notions of information and distinguishability in quantum mechanics. And so if you're going to work with mixed states, you need something that's going to play the role of the inner product, or is going to be able to carry that burden. And just writing down some arbitrary metric is probably not going to be the best idea. And so I'm going to give you 2 examples, and there maybe one more will come in a little while later, of functions that are that morally play a kind of similar role to the inner product. And the first one is the fidelity, and it really is a generalization of the inner product. And so if you have two mixed states, rho and sigma, and I put little subscripts A on them because that's going to be convenient here, indicating that they're states on some system A, then the way the fidelity is defined is by saying, well, we have the inner product, so let's try to use the inner product. So let's convert these mixed states into pure states. And so it's going to be an inner product between a pure state associated with rho and a pure state associated with sigma. And those pure states are going to be on a composite system now. So it's going to be a state not just on A, but on AB. And phi rho and psi sigma are going to be what we call purifications of rho and sigma. So what does it mean to be a purification? It means phi rho is a purification of rho, meaning that we get rho back if we trace over the B part of phi rho. So it's a pure state that is rho on the appropriate subsystem. And likewise, if we trace over B for psi sigma, we'll get back sigma. And so that's what it means to be a purification. And the way that you define this fidelity is just by saying, well, maximize over all possible purifications. Do your very best to align these states. And you might ask, well, why the maximum instead of the minimum? If you make it the minimum, you can always make the states orthogonal just by putting two orthogonal states inside this, inside the B system. And so the appropriate notion, the useful notion here is to maximize. And oops. I'm just going to bring up the participant list in case anybody raises their hand rather than jumping in. Okay, so why is this a useful measure? Let's just start by enumerating a few of its simple properties. How big can it get? Can anyone tell me the largest possible fidelity between two between two mixed states? Like numerically, how big can this get?
Should be 1.
Yeah, it can be 1. So it can be 1. And what's interesting is that it will be exactly equal to 1 if and only if rho equals sigma. All right, so that's like for pure state quantum mechanics with the inner product. And how small can it get? You just shout it out. Or dump it in the chat.
0.
Sorry?
0.
0, right? It can be 0. And again, as we would hope, it will be 0 if and only if. Well, what would the desirable notion be? So I'll unscroll this here. It will be 0 if and only if there is a measurement capable of distinguishing rho with sigma and never making a mistake. And what does that mean? It means if we take the non-zero eigenspace of rho, it should be orthogonal to the non-zero eigenspace of sigma. So there's a projective measurement that will be able to just tell them apart. And so I'm writing that as the rho perp symbol sigma. And mathematically, you can test that by just asking, by just verifying that the inner product trace rho sigma is 0, because rho and sigma are positive semi-definite. So, so again, so the fidelity, at least in this sense, is doing the right kind of thing for us. But we might want a little bit more than that. So it's supposed to be a measure of distinguishability. And now suppose that there are two painters, and painter 1 has her palette, some collection of colors, and painter 2 has his palette, some collection of colors. And now imagine that they each take their colors and just smear them on the canvas. Was the situation more distinguishable at the level of the palettes or at the level of the smear? Or if the smear is just taking all the colors and mixing them together into a circle or a disc, if that makes any sense. Just write it into the chat. Is the smear more distinguishable or the original carefully chosen palettes of colors? I think my example, which I invented on the fly, is not the best example. But what I wanted to get at, the original is more distinguishable. Thank you, Al. Thank you, Annie. Okay, so if you mix paints, you're likely to end up with brown or black, regardless of the particular details of the paints that you chose at the beginning. And the same is true of mixed states. We would intuitively expect that if we had some collection of density operators, maybe weighted with probabilities, that if we could distinguish, if we could try to distinguish them before mixing, that they would be more distinguishable than they would be after mixing. And that will manifest itself as a convexity property, in fact, concavity of this fidelity function. So the probability weighted fidelity of rho j with sigma j, so some probability weighted ensembles of mixed states, will be less than or equal to the fidelity of the average states. Right? Just like the smeared brown is less distinguishable than the original choices of palettes. And so I drew that, it's concave, right? So I hope that picture, you know what I mean by concave there. And one last property that I'll mention, and so it's quite common in quantum information to define quantities that we're interested in using maximizations over various sets. And that has the nice property that they often have some conceptual significance or utility, but that also makes them hard to calculate with. Now, the fidelity is nice because not only does it have this nice conceptual definition in terms of this optimization, but it has a pretty straightforward formula without the optimization. So you can evaluate that optimization directly and get a formula like that. So the fidelity is the trace of the square root of the matrix product rho 1/2 sigma rho 1/2. And I'll just remind you that the rho and sigma are positive semi-definite operators. So they have a well-defined square root where you just take the square root of these non-negative eigenvalues. And rho 1/2 sigma rho 1/2 is itself also positive semi-definite. So you can take the square root of that without ambiguity. And so the fidelity, we'll use this formula for the fidelity function at some point later today, depending on how quickly we manage to go. I'll stop there. Are there questions about the fidelity before we keep going?
Is this concavity condition like related or the same in any way to like a data processing inequality?
It is a special case of, yeah, we'll talk about monotonicity in just a little bit, but it's a special case of monotonicity, okay. Data processing. Yeah.
Thanks.
It corresponds to, we can get to it later, but if you had an additional register, like a classical register that was keeping track of J, that would give you the left-hand side of this inequality, and you throw away that register, then the monotonicity tells you the fidelity should go up and you look at the right-hand side. Okay, so the fidelity.
One more thing on that last page.
Sorry?
Can I ask one more thing on the last page? I'm wondering why the paint example and this inequality, why did we bring that up?
This one here? Sorry, this one here?
Yes, yeah.
Why do we bring it up?
Like inferring something.
Well, I'm going to use it later.
Okay.
But yeah, I'll say I'm going to use it later. And I wanted to tell you, this is a little bit, so this course is supposed to be an overview of quantum information, which is a pretty big field. And so I wanted to highlight, I'm trying to highlight for you the things that you're likely to see or need at some point. And this is one of those basic properties of the fidelity function. And it's related to this notion that just came up of monotonicity, that under physical transformations, as we'll see, fidelity should only increase. And forgetting J is one such transformation, if something that could physically happen. So the fidelity is nice, but one thing that it does, and you can use it as a kind of measure of distance, but you'd like to be able to say that if state 1 is close to state 2 and state 2 is close to state 3, then state 1 is close to state 3, right? That you just like to have some triangle inequality type property available, and something like that does ultimately hold for the fidelity, but it's a bit more complicated. So So what I'm going to do is I'll introduce an actual metric on the space of states, the trace distance. And it's going to be written in terms of this, this norm, which I'm going to write as a norm symbol subscript 1. And the way it's just defined is we're going to sum over the eigenvalues of x, absolute value, right? So it's the L1 norm of the eigenvalues, and more generally, if x is not diagonalizable, the singular values of the matrix. And we'll talk more about the singular value decomposition actually tomorrow, but this is called the Schatten L1 norm. So it's just some norm, and it would seem pretty arbitrary to you, but I'm going to try to justify why this is a good one. And once you have a norm, you can define a distance, right? So the distance between two states, rho and sigma, is this trace norm of their distance, or of their difference, I should say. And we'll just go through the same exercise again. What properties does this have? Well, it can be as small as 0. And the norm is 0 if and only if its argument is 0. And so as desired, the distance will be 0 if and only if rho equals sigma. And maybe I'll ask you, how big could it be? How big could this thing get?
Infinite?
Well, let's talk about states that are density operators of trace 1, right? So it won't actually get infinite.
So maybe 1.
Close, 2. So if the two states have orthogonal supports, then you'll get a trace of, you'll get a 1 from each state, and so it can get as big as 2, and it will be exactly equal to 2 if and only if rho is perpendicular to sigma in the sense that I gave before. And so it's doing kind of the same thing as the inner product function, or the fidelity function. And just as we discussed before, mixing states should make them less distinguishable. And that means the inequality should go the other way compared to what was happening with fidelity, because fidelity was a measure of how close things are. This is a measure of how far apart things are. And yeah, go ahead.
I mean, this rho perpendicular to sigma, what is the like relation, like what algebraic equation gives says that rho is perpendicular to sigma?
It's the condition that the non-zero eigenspace of rho is perpendicular to the non-zero eigenspace of sigma.
I see. The two vectors are perpendicular to each other.
Sorry?
The non-zero two eigenvalue vectors are perpendicular to each other.
Yeah, exactly.
Okay.
Yeah. And you can test it because these are positive semi-definite matrices. You can test it by just evaluating trace rho sigma, right? So if it's equal to 0, that tests that confirms that their eigenspaces are orthogonal. They're non-zero eigenspaces.
Definitely. This trace calculates that dot product. That's true.
Mm-hmm. Okay, now what's really nice about the fidelity and what singles out the subscript 1, the Schatten L1 norm, the trace norm, is that this is actually an operational measure. It's really the measure that tells you whether two states are close in a useful sense when you try to actually perform a measurement. Because you can actually evaluate it by taking the maximum over, say, observables O that have the property that the largest eigenvalue of O is less than or equal to 1. So this is a normalization condition on my observables. And I just take the trace of O rho minus sigma. So if you're wondering where this comes from, this is just a special case of LP duality, L1 and L infinity. You can, in fact, it follows from that in the case of these Hermitian matrices, but you can take it otherwise just as a statement of fact. And if you expand this out, what is this? This is saying that the maximum over observables with this norm condition, and I'll just write the norm condition in the way that we usually write it, that the Schatten L infinity norm is less than or equal to 1. Just in this case, is that the largest eigenvalue is less than or equal to 1 of the expectation value of the observable for rho minus the expectation value of the observable for sigma. And so the trace distance is really telling you, find the very best observable that you could ever imagine for telling these two states apart. And what the trace distance tells you is the maximum difference in the expectation values that you can achieve if you find the very best observable for telling two states apart. And so operationally, if you were trying to come up with an operational measure of distinguishability, you'd probably start right here, right? This would be a good, this would be a good definition. And then you could work backwards and then find out, actually this, mathematically, the answer, that quantity that I wrote down is this one up above. And so the trace distance is really the best operational measure of distinguishability of two quantum states. Now, you might be tempted when you're working with density operators to do something like calculate the Hilbert-Schmidt distance, right? It's easy to evaluate, something more like, use this kind of norm, right? Because that's something that that's something that's super easy to calculate because it's the trace of the square of something. Whereas this norm here is something more complicated. But I'll warn you that this other thing that you could write down, it can be convenient sometimes to calculate it, but operationally it doesn't necessarily mean very much at all. And so you should be careful if you start measuring the distance between density operators using some ad hoc norm, that the notion of close, how close you are and how far you are that you get out of that may not mean very much physically. So that's just a warning.
Can I ask a quick question?
Sure.
What does the infinite subscript mean for the norm in the last line? For the operator rule?
You mean this subscript right here? This one?
Yeah.
Yeah, so why don't I just I could just say that in general, so this is equal to so if you take the singular values of x and evaluate their LP norm, this one here, then that gives you this Schatten LP norm. And so I just mean, that's all I mean. And in this particular case, it just works out to the L infinity norm of the eigenvalues. And that is actually, it is exactly the same thing as this largest eigenvalue. So I could have just never introduced it, but I decided to introduce it just because you'll see it. If you ever read quantum information papers, you'll see these norms flying around, and you might as well know what the notation is.
Could I ask another question? It's not very important, but I always was confused by fidelity being written as like square root of rho sigma times the square root of rho instead of just like square root of rho times sigma. Do you have an intuition for like that?
Oh, well, rho times sigma is not Hermitian. And so then you run into issues of diagonalizability and so on. And so it's just, it just keeps everything simple if you just say rho and half, sigma, rho and half. Yeah.
All right. Thanks.
Okay. And
sorry, again, regarding that, how do you show that f or a sigma takes that form with a trace of the square root?
Sorry, I didn't quite hear you. Could you repeat the question?
I just wanted to know, how do you show that the fidelity is a trace of the square root of?
Oh, how do you show that? Okay, well, I'll defer you. I'll suggest that you go back to Preskill's notes. It's going to follow from some games with the polar decomposition, and like there's work that you have to do there. Like there's it's not a totally trivial statement. Yeah.
Okay, great. Thank you.
Yeah. Okay, so I'm going a little bit slowly, so I'm gonna skip over a few things. I won't write this down explicitly. Morally, trace distance and fidelity, they're not exactly the same, but if one is small, the other is small. And so you can check, well, I don't think we're going to have to use that. Well, I'll write it in. Why not? 1 minus f less than or equal to trace distance over 2 less than or equal to fidelity, 1 minus fidelity squared. And in particular, there are no dimensional factors in these inequalities. So it's really just a true statement. If you're close in the fidelity sense, you're close in the trace distance sense, and vice versa. And now the last really important property that we alluded to earlier is this monotonicity property that applies to both the fidelity and the trace distance. And so if I had the fidelity of two density operators rho and sigma, I could compare it to the fidelity between rho and sigma after they've both gone through some quantum channel. And quantum channels, we call these noisy quantum, they're noisy quantum channels, so they could, they don't necessarily have to directly introduce noise, but they involve, as we saw, adjoining some environmental system in a pure state, applying a unitary transformation, then tracing over some degrees of freedom. And that step of tracing over degrees of freedom, we would generally expect that to cause states to be less distinguishable. And that's exactly what happens. The fidelity goes up, right? The states become less distinguishable. And similarly, the trace distance, the inequality has to go in the opposite direction because it's a measure of distinguishability. And this is also a hugely important property if you're going to reason about distinguishability of states. This monotonicity, you use it all the time. And it again, if you write down some ad hoc measure of the distance between two quantum states, or how close they are, you should not expect it to satisfy this monotonicity property. The monotonicity is something very special and pretty hard to achieve. And so this is another reason that these are privileged measures of the distance between quantum states. Okay. And so now on to entropy. You encounter entropy, at least I first encountered entropy in my classes in thermodynamics. And we were first exposed to entropy before we did StatMech. And it was one of the most mysterious, puzzling concepts that I'd ever encountered, not just in physics, but anywhere. StatMech cleared up quite a bit of the mystery about entropy. That it was really associated with state counting. And at the end of the day, that's really what uncertainty is, right? Or rather, what entropy is. It's some function that measures uncertainty. And there are actually many different notions of entropy that one can come up with. And we'll see a few of the different notions of entropy over the course of today and maybe tomorrow as well. So, and what should I say about them? And we're also going to ultimately talk about information. But to understand what information is, first you have to quantify uncertainty, because somehow information is whatever reduces uncertainty. The gold standard measure of uncertainty, in many ways the best one for a huge number of different reasons, is this von Neumann entropy. And the formula, it's a function of a density operator. Because remember, a density operator is a mixture over quantum states. And so there's some uncertainty associated with the density operator just because you don't know which pure state you have. And the formula is just minus the trace of rho log rho. And we just define 0 log 0 to be 0 here. And you may have heard this, but there's a funny story about the von Neumann entropy. Von Neumann wrote this down in 1929. And around 1947, he was talking with Claude Shannon. I guess I'm getting this a little bit backwards. But Claude Shannon, who's the inventor of information theory, wrote down this function for von Neumann and said, I've encountered this function when I've been studying in information. I think it's an interesting function. And von Neumann told him, oh, you should call that entropy. And so we often think of the von Neumann entropy as being a generalization of the Shannon entropy of information theory. But von Neumann wrote it down 20 years before Shannon wrote down the classical special case. And we're just we seem to be playing this game. If you see new functions, you want to have some intuition about how they behave. It's supposed to be a measure of uncertainty. The way it's constructed, it can be as small as 0. Can anyone propose a condition under which it might be reasonable for this to be equal to 0? When is there no uncertainty?
Single state?
If it's a pure state.
Yeah, exactly. So if and only if rho is pure, which means is the statement that its rank is equal to 1. And it can get as large as the log of the dimension. I'm writing D here for the dimension of our Hilbert space. And what do you think is the most uncertain state you could actually have in a D-dimensional Hilbert space? How uncertain could you be?
1. Maximally makes 1.
Yeah, exactly. So if you took the uniform distribution over all states, right? So the unitarily invariant distribution over all states, and you look at its density operator, that will be the state which is proportional to the identity matrix. So we have equality if and only if rho is the identity over the dimension. And so this is measuring uncertainty in that sense. But as information theory, I'm an information theorist, we often aren't satisfied at just writing down functions that have nice properties. We want to have some operational interpretation of what it is. And there's some intuition that you might get from statistical mechanics or elsewhere, that this entropy controls the effective rank of the state. That you'll hear people say, oh yeah, well the effective dimension is roughly e to the entropy or something like that. And that statement is often true, but it need not always be true. I'll tell you about a situation in which the entropy really does control the effective rank of a state. So we'll consider a state, I'll write it rho tensor n, which is the n-fold tensor product of rho. So the reason I'm writing down this n-fold tensor product is basically because under the hood of what I'm going to do, you're going to have to use the law of large numbers, and this is a nice way to get the law of large numbers to act. Something very similar to what I'm going to say is true, say, in 1+1 dimensional CFTs, or more generally in holographic theories, and under some pretty weak assumptions in quantum field theories as well. And so this rho tensor rho uncorrelated many copy situation is easy to think about, but the statements that I make are going to be true in situations of physical relevance as well. So what might it mean for the effective dimension to be controlled by the entropy? Well, it could mean that there's a projector and that the rank of that projector, so the rank, is controlled by the entropy. So is e to the n times the entropy of rho plus something subleading, little o of n. So there's some projector, and the trace of that projector against the state is large. All right, because that tells me that the quantum state is effectively contained in the non-zero eigenspace of that, in the range of that projector. Now, to make this a bit more precise, we should introduce a few more quantifiers. We should say that for all epsilon, there exists an n sufficiently large. So if you take enough copies, there exists this projector that we're talking about. So roughly speaking, in some kind of thermodynamic limit, there really does exist this this subspace that is exponentially smaller generally than the ambient Hilbert space that contains the quantum state that we're interested in. And so we'd say we can compress. 1 second. We can compress our state to the support of this projector. Now we can also think of this a little bit. It will be useful today and in future days to think of a quantum of a unitary transformation that could actually implement this this compression operation. And so if we have many copies of this quantum state rho coming in, then there will exist some unitary, and the unitary will have two outputs. I'll call them T and T bar. And T is the part that we're compressing to. So the dimension of T will be about E times the entropy. And I'll just drop the little o of n part. And what's interesting about this when you think of compression in the context of quantum mechanics is that unitary transformations don't generate any additional uncertainty, right? And so you can actually set up this unitary transformation so that the other output of the unitary transformation is approximately pure. And so if you try to implement compression unitarily, what you find is that you implement a kind of refrigerator. You implement a way to actually not just concentrate the uncertainty in the state, but you also concentrate the certainty. And this observation has actually been used even experimentally as a method for cooling systems in NMR and improving the contrast in NMR experiments. You actually you compress the noise into some degrees of freedom, and then the others will be pure and will give you higher contrast in your experiments. Okay, so are there questions about my little introduction to entropy, what it means, how it's associated with compression? If not, I want to make a little aside that if you ever hear quantum information theorists speak, they'll say things like, Alice sends some quantum information to Bob. And that language is, if you're not initiated to this little priesthood, it can be pretty confusing. So I want to just talk about what it means to send quantum information. And so let's think about a situation. So in this diagram, in all these diagrams, time is going from left to right, and the purple lines indicate some quantum systems. And we'll start out with a pure state. So let's call the top system R, the bottom system A. And we'll start off with some pure state. We'll call it psi RA. And then some channel X, and I'll call the channel C. Oops. And we could imagine, we could ask about the situation where what does it mean if the channel is able to send half of the entanglement of the state psi? So we could do it perfectly, but we've now been exposed, and we have some familiarity with different notions of distance for quantum states. And so if it doesn't do it perfectly, what we could say is it sends it with high fidelity. So maybe the fidelity is at least 1 minus epsilon between the state that went in and the state that came out. So it acts as the identity channel on R, the channel C on A, and acts on psi RA. Maybe I should even call this B here for good measure. So if this channel is able to send this one single quantum state, you could ask, how much can you learn from that, right? Like in general, if I'm able to send one quantum state, that might not seem like a very strong criterion, right? That if you have a telephone, saying that your telephone is able to send information, it's not enough to be able to send a single symbol, because that single symbol in and of itself doesn't actually contain really any information at all. It has to be able to send a multitude of different signals that you can actually get some information across. But sending half of an entangled state ends up being interesting. And the reason is that we have this monotonicity property of the fidelity. And so if I choose any channel I want, I could degrade the R system. I'll call that the reference system. So if I degrade the reference system, the fidelity can only go up. Okay. So that's just a monotonicity in action. But I could, I can choose any channel I want for this degrading D. And what I'll actually choose is a channel D of rho that is the dephasing channel, the one that we saw last day that zeroes the off-diagonal entries of the density matrix. So I choose some basis of the R system. Oops. And I just zero all the off-diagonal entries in that basis. And that's that channel D right there. And that actually, I'll tell you where we're going with this. By virtue of this monotonicity, what we'll see is that if I can send this one single entangled state through the channel, that means that I can send a very large number of ensembles of pure states through the channel, such that on average, the fidelity of is high within the ensemble. So just to see how that works, let's just take the entangled state psi RA of the R system and the A system and expand it. So I'll expand it in terms of in this basis J of the R system. I can always, I think I called that chi. I can always expand like this, provided I allow myself to use unnormalized states chi j that aren't necessarily orthonormal or even orthogonal. And let me just normalize those states and pull out the normalization factor like so. And so this is a completely general vector of a composite Hilbert space that I've just expanded in terms of an orthonormal basis on the R subsystem. And now let's just apply the monotonicity property. So this monotonicity statement here, if I apply the dephasing channel to this quantum state, it's going to take this superposition and turn it into a probabilistic mixture, where it will be a probabilistic mixture over J's with probability weights J. And so what it looks like is a sum over J, probability J, and the system R is going to be just in one of the different orthogonal pure states labeled by J. Not in a superposition, just a probabilistic mixture. And the A system is going to be in the corresponding density operator, like that. Now, on the other side of the fidelity function, oops, it's still going to be a probabilistic mixture over J on the reference system, and then the channel acting on chi j, like that. And so this looks like a beast, but now we can use the formula that I told you about for the fidelity. So it has all these matrix square roots in it. You might think that's a horrible looking thing, but one thing that you can see immediately from this formula is that if rho and sigma are simultaneously block diagonal, then the fidelity is going to be a sum over pieces, contributions from each of the block diagonal blocks. And the state that I have up above here is block diagonal with respect to J. And so what I actually get out of this is a sum over J, probability weighted, the fidelity of chi j against the channel acting on chi j. Like that. And so verifying that you're able to send a single state, right? A single entangled state tells you that you can send a whole family of pure states through the channel, and on average, how should we say? I'll say this precisely since it's a bit of a mouthful. If I send a pure state, I can look at the density operator of that pure state on the A system, and the ensemble ambiguity property that we've discussed a number of times tells us that there are an infinite number of different ways to expand that density operator in terms of a mixture of pure states. And what we found is that the channel is going to send those ensembles, is going to transmit those ensembles on average with high fidelity in every single case. So regardless of the ensemble that you choose, when you expand your density operator, it's going to go through the channel. It's going to be transmitted with high fidelity. And so this is an illustration of how you use the fidelity function, how you use monotonicity, but also it's an illustration of the fact that the notion of sending, when we say sends quantum information, we often just verify that by saying, check to see if the channel is capable of sending half of, say, a maximally entangled state. And if it does, then it sends pure states on average with high fidelity. Anyone want to ask about that little calculation?
Can you say something about epsilon? Like, did we relate it to one of the parameters of the channel? Or
oh,
no?
so you can, yeah. So I'm just saying hypothetically, yeah. This is sort of a suppose the channel can send psi RA with fidelity 1 minus epsilon. So it's, maybe I should even just say, maybe I could just, maybe a better way of saying this would be to define epsilon as that fidelity.
Okay, thank you.
Yeah.
Just a question. I missed why would the states not equal to psi RA have high fidelity? I understand that the fidelity, after you apply D, the fidelity increases, but I don't understand why should it still be high? Decrease, why should it still be high?
Why it should still be high?
Yes.
So this, I mean, on the one hand, it's just a property of the fidelity function, right? That that fidelity can only increase with, like, if you post-process, like you have some pair of states, you look at their fidelity.
Oh,
if you then
sorry,
apply
I
any
think
channel,
I think it was just my intuition was wrong. So high fidelity means the states are close, not
exactly
further away.
Yeah.
Okay, sorry.
That's
thanks.
all. Okay. Okay, so let's think about this a little bit in the context of compression. So here what I have is the compression circuit that we talked about before, that there's a density operator rho tensor n on A tensor n. You put it through this compressing refrigerator, but now you discard the part that was pure, and you're left with the compressed part. And so let's just introduce the channel that goes from the input to the compression. We'll call that C. It's both channel and compress. And we can choose any purification we want for rho tensor n. So let's just call the purification phi rho tensor n, and it's on n copies of the reference and n copies of A. So, and what I told you about before is the fact that we can compress to this T system in the sense that there's a projection that captures almost all of the support of rho that comes out, or that and whose dimension is the appropriate size. In this circuit picture, we can make the notion of compression a little bit more operational by saying, well, actually, we can even take the compressed system and apply some channel, and we'll call that our decompression channel. And actually, it's not even just a channel. It's something simpler. It's morally unitary, but it can expand the dimension. And so it's just a matrix that preserves inner products. And let's call the quantum state that comes out sigma. So it's going to be sigma on n copies of the reference and n copies of A. And what we actually achieve when we compress is that the fidelity between n copies of the purification of rho and n copies of the compressed and then decompressed quantum state is going to be larger than, say, this 1 minus epsilon. And that will even be true, based on what I just told you about before, not just for this single purification, but for any decomposition of rho into pure states. And so if I decompose rho as some sum over j, pj chi j, then what we, by the discussion just that we finished up above, the fidelity on average between the chi j's and the decompressed and compressed chi j's is going to be larger than 1 minus epsilon. All right, so, oh, whoops, this should be rho tensor n. So if you decompose the density operator into some pure states and then compress and decompress, on average over the states in that decomposition, the fidelity will be high. And so it turns out that this statement follows from this statement about this projector. The statement about the projector was proved by Petz in the 1980s. The realizing, kind of placing it in this operational framework was done by Ben Schumacher in the mid 1990s. And so we refer to this as Schumacher compression, but it should perhaps be PEPS, Schumacher-Petz compression or something like that.
I guess how would you choose the best choice of decomposition that, like, say you want this to be like as large as possible? Is that easy to do? Or?
Well, the choice of decomposition, it really is more something that might be given to you. Like if you're going to try compress in a given situation, you might be in a situation where there's some source that's generating particles, right? And you might say, well, I want to compress whatever's coming out of that source. And so it's not under your control what rho is, and even the states of the decomposition. But the part of the message here is you don't need to know what the ensemble is. You don't need to know what the purification is, because you just apply there's one compression procedure that works in all cases, and it will always do the job. And so you can be completely oblivious to the details of rho. And I guess I could go a little bit further. This goes beyond this, but in fact, there are compression procedures where all you need to know is the entropy of rho. You don't need to know anything about its eigendecomposition or anything else, and still be able to compress effectively. And so there are what we call universal compression procedures that are actually very powerful ways of shrinking down the Hilbert space, just under some symmetry assumption of the state. You just need some, maybe you need to know its entropy and some symmetries, and then you do your compression.
So I guess for the fidelity measures where it's like written as a maximum over like the best decomposition, like I guess sometimes you don't actually know what that is.
Oh yeah, so the fidelity measure, so maybe you could also be asking, how would we even know that we have achieved this if we don't know the optimal purification? And the statement is more of the type, given the density operator, I'll tell you how to compress it, and it's a theorem that I'm going to achieve this F. I'll be able to tell you exactly, exactly what the errors are. I could go on at length about not just the leading order error, but the second order, third order. Like all these things are known in great detail. And so, what you get is a guarantee that the compression was good, and then you can use it for whatever purpose you want.
Okay, thank you.
Yeah, you're welcome.
Can I ask another question before you go?
Sure. Yep.
I guess my question is, could you help me understand this by putting this into kind of like a physical picture of some experiment that we're doing? Because I guess I'm just having a hard time seeing like how you're actually, like, what are you going to do to actually construct one of these channels? Like, what would this physically be?
Yeah, sure. So, so the compression, let's see, it would, in order to implement, like if you're actually going to make it happen, you would probably need a quantum computer. So this U here would actually be, if you had a quantum computer, there'd be a bunch of qubits. You would have some restrictions on how they could interact. Maybe you could apply arbitrary unitaries on single qubits, and maybe on pairs of qubits. And then I would decompose the actual unitary that performs this transformation into a series of gates, and you'd run them on the little quantum computer, and then you'd shrink. There'd be some information that comes in, and you'd shrink it down to a smaller, into less information. Just like if you run zip on some files on your computer, right? It comes in big, it comes out small, it uses fewer bits. Now, in the context of this course, you're not going to bother actually running this on a quantum computer. What you actually really care about more is this notion of effective Hilbert space dimension, right? That's actually a very useful notion physically. And so the message to take away would be, say you have a density operator that you've encountered in holography, for example, and it has finite entropy. Then what it really means is that there is it lives in some infinite dimensional Hilbert space, but has finite entropy. There is a finite dimensional subspace of dimension roughly e to the entropy that contain, in which that density operator is not exactly contained, but is effectively contained. Okay. And so you can project on it, or you could use a circuit to extract the information and compress it to some smaller number of qubits, but that the system it's not just it's giving some meat to the statement, that you might have some intuition about about it being roughly finite dimensional. Like you can really actually make it finite dimensional.
I see.
Yeah.
Okay. Thank you.
Yeah, you're welcome. Okay, we're going to talk now about relative entropy. And relative entropy is the source for it is the function, the source of all of their entropies, and it's going to look strange to you because it probably isn't a function that you've encountered before, but it has as special cases the von Neumann entropy and lots of other things. And it's defined in this funny looking way: the trace of rho log rho minus the trace of rho log sigma. Oh, actually, I apologize. Before I move on, I should just point out, I'm going to rewind all the way here, that in this community, not in quantum information, but among high energy physicists, von Neumann entropy is often referred to as entanglement entropy. Sometimes it measures entanglement, sometimes it doesn't. It always measures uncertainty, but you should just know that if people say the word entanglement entropy, that's what they mean. Now, going back to relative entropy, trace of rho log rho minus the rho log sigma. We already covered two measures of distinguishability in this course today, and you might feel that you don't need any others, but we do need another measure of distinguishability, and this is the reason. That if I have two orthogonal, or not orthogonal states, but I have two states of, say, a single qubit, right? One of them is maximally mixed, and one of them is pure spin up. Then their fidelity is is somewhere between 0 and 1. Their trace distance is somewhere between 0 and 2. But if I had two fairly distinguishable states of, say, our solar system, they would also just have fidelities and trace distances somewhere between 0 and 2. Or for that matter, let's say we talk about orthogonal states, right? Orthogonal states and fidelity are at most orthogonal. But intuitively, somehow, we feel that if we have a large number of degrees of freedom, and all those, and there's distinguishability in all those degrees, all of those degrees of freedom. So imagine that we took all of the matter in our universe, and we flipped all of the spins and all of the atoms in the universe, say in our solar system. We would think that somehow that it would be a more distinguishable situation than just flipping one. But our earlier measures don't really do a good job of capturing this. The relative entropy is going to be a measure of distinguishability that can get bigger and bigger and bigger as the system gets bigger. And so it's still going to be true that it will be 0 if and only if rho equals sigma. But it can actually get as large as being infinite. And it's both a virtue and a defect. It's actually very easy for it to get infinite because of the trace of rho log sigma piece. That log of 0 or a log of 0 can easily give you something infinite. So if the support of rho is not contained in the support of sigma, then this thing is infinite. And in particular, it's infinite if you just have two pure states that are not the same. Even if they're not orthogonal to each other, this thing is going to be infinite. And so that would seem to be a defect, but it's an extremely useful function. It satisfies monotonicity, right? So the distinguishability can only go down if you apply quantum channel. I should say that it's not very hard to prove monotonicity for the fidelity. In fact, it's trivial for the fidelity. It is easy enough for the trace distance. For the relative entropy, it's pretty hard. It was even a conjecture for several years before it was proved, but it is proved. And it also has a nice converse, the data processing inequality. So you could ask, under what circumstances does distinguishability not go down when you apply quantum channel? And the answer is it doesn't go down only if you can undo the noise. So only if there exists a channel such that if you apply the channel after applying the noise, it's the same as if you'd done nothing. And we're going to talk about quantum error correction probably starting next day, but you can imagine that this might have something to do with quantum error correction, being able to undo noise. And it's even true in an approximate setting. And that was only demonstrated a few years ago, that if the monotonicity is almost saturated, but not exactly, so we have near equality here instead of strict equality, then there exists a channel that will almost reverse the noise in the fidelity sense. And that's something that actually played an important role in the theory of entanglement wedge reconstruction, and you can look that up in the reference there. Now, we don't have a lot of time left, but we have a bit of time for you to start on today's worksheet. And I'll just let you break out into the into groups at around 2:15. I won't bother calling you all back today, but I'll send around a message at around 2:15 that we can you can shut it down if you want to and move on to gather. And what you're going to do in the worksheet, you're going to see this relative entropy function, which is something that doesn't look at all familiar if you haven't seen it before. Trace of rho log rho minus trace of rho log sigma is actually something very familiar. In the context of thermodynamics, it's free energy from the it's the free energy difference from the free energy of the thermal state. And so it's a very natural function in physics. And you're also going to prove something called the first law of entanglement entropy, which has played a large role in understanding. Well, we'll talk about that a little bit more next day. But I'd better let you go. So let's start the breakout rooms. Let's see. We'll have 10 breakout rooms. Okay, so I'll let you go give that a try. I'll give you some time to finish it at the beginning of next day as well, because you don't have a lot of time right now. And on that note, off you go. Remember, you can download the worksheet from the wiki.
Wasn't sure if we were going to attempt the breakout rooms with 5 minutes left or not, but I guess they can get started.
Yeah, I guess so. We did it a little earlier yesterday, and he came back after it, but I guess we're not going to come back after it today. Alex, how are things going on your end? I'm not hearing anything.
No, me neither.
Okay.
Okay.
See your chat. Okay. Well, so far it seems, from my point of view, like, I mean, I hear everything getting recorded because I hear the announcement. So it seems like things have been going all right. Appreciate your efforts so far. And the first few days are always the hard stuff getting in. So I think you might as well stop the recording because Patrick said, yeah, there's only 3 minutes left. And he said, we're not coming back.